This talk is about perturbations in livestock time series. Within the field of precision livestock farming, we move at the scale of an individual animal from which we get data that we want to translate into useful information. The next step is to integrate information into knowledge, allowing to take decision and perform an action on this individual animal. For instance, data can be milk progesterone in dairy cows. Information is a drop in progesterone. Knowledge is ovulation timing, and action is insemination. PLF has primarily developed through the automation of data acquisition. And if we look back 100 years ago at, for instance, milk yield data, we can see clearly how moving from small to big data has changed our way of addressing lactation dynamics. Topics have changed from considering theoretical curves in textbooks with the aim of removing variability around the average animal to infer standard profiles, to observing on-farm real dynamics, analyzing individual variability and focusing on perturbations, like this one in dairy goats lactation data. Here, a quick look is enough to say, well, something wrong happened here around 100 days after calving, and many questions can arise. Did all animals from the herd have this drop in milk at that time? In the same way, can we see the same drop in intake, in body weight? Is the way milk drops and recovers tells us something about this animal? If we would have been able to detect the start of the drop, things would have been different? So why focusing on perturbations? To analyze variability and compare animals and gain insight on performance determinants, to provide metrics for concepts such as resistance, tolerance, resilience, robustness, plasticity, efficiency, to generate benchmarks for decision support, and make it possible to provide early warnings. Okay, what do we need to detect perturbations? We need interpretive tools to transform data into information, generic tools to gather and integrate information into knowledge, and real-time tools to make it possible to use this knowledge for action. For a couple of years, we have started discussion with an emerging and open group of modelers interested in and working on perturbation. Thanks to Mazume, Ahmed, Raphael, Laurence, Nick, Ines, Ben, and Mati, I am very happy to give you today a few comments on where we are and where we want to go. First, we share a main rationale considering that a perturbation in time series can be seen as the response to a disturbance and as a deviation from a theoretical expected unperturbed dynamics. This view is a starting point. An expert in signal processing may not be very comfortable with this view, but from a biological standpoint, this view relies on the classical concept of a potential genetically driven trajectory and echoes the physiologically based fundamental properties of homeostasis, which is the long-term tendency to homo on to a trajectory, and homeostasis, that is to say, the short-term tendency to restore equilibrium. Until now, we and others have worked on various species, including cows, goats, pigs, and fishes, on different variables related to production, physiology, and behavior, and in contexts where we know or not the origin of the perturbation. Things are not the same when we know the time at which a perturbation is expected, for instance, during an experiment with a controlled nutritional challenge, and when we know nothing and we just try to detect if, when, and how things went wrong. No time today to get into details, but here is a big picture illustrating the diversity of mathematical and computing methods that have been proposed, from differential equation to particle filters. We can distinguish two major families of approaches, either concept or data-driven. Concept-driven approaches are based on an a priori logic or model used as an analytical prism to interpret data. For instance, with Sadoul a few years ago, we proposed the analogy of a dam spring system to model perturbations. Data-driven approaches are based on methods, processes, algorithms, and systems to extract insights from data. For instance, Ben Abdelkrim used smoothing methods to detect perturbations. And this is a continuum. Somewhere in between, Frigens and al. Used a piecewise statistical mixed model to do the job. We strongly believe that there is not one approach better than the other. Another major difference between approaches is the way the perturbation is considered, either with an explicit model of each perturbation. This is the case in the work of Gomez and Ben Abdelkrim, introducing a perturbation lactation model, or without explicit modeling of the perturbation. This is the case in the work of Adriens. Using iterative fitting, a perturbation is detected when residual errors deviate too much from expectation. To be mentioned, these two approaches use the same classical model of Wood to build the unperturbed curve. Sorry for those unfamiliar with lactation curves, but this is the subject I am the most familiar with. Other differences exist between approaches. Some works online, other offline. They can be suitable or not for multivariate analysis. About that, we believe we have a lot to learn looking at how synchronous are perturbations in different time series. Here, milk yield and body weight, again in dairy cows. Approaches can include parameters with or without biological meaning. They can be greedy or not in computing time. They can be generic and flexible versus specific and sensitive. I will stop here. The point is, as usual, take the right tool for the right job. But we want to go a little bit further. We think that the future is hybrid, and we want to think about combining approaches to link data interpretive tools with knowledge integrative models. The idea is that pure biological concepts mix very well with pure numerical methods, and to link online and offline methods that can feed each other. In the end, we also believe that modeling perturbations can provide metrics to link performance and health and welfare. And we started to build a project called Perturbations toward fast and smart IT tools. The main originality of this project relies on using modeling and computing approaches as a transdisciplinary framework to generate an interdisciplinary network around a common issue, perturbations, which are, for modelers, a dynamic pattern to be modeled, for animal scientists, a performance loss to be quantified, for epidemiologists, a health indicator to be inferred, for behaviorists, a welfare criteria to be assessed, for computer scientists, an early warning to be detected. Thank you for your attention. And as requested by Mona, here's a slide for opening discussion with three fundamental questions. How far are we from reality with the idea of a theoretical, expected, unperturbed trajectory? Could this trajectory be affected itself by perturbations? And ultimately, could perturbations be themselves part of the normal process?